Hello everybody. Alrighty, so it is 5 o'clock and I anticipate a lot of people will be coming in semi-late here, but I think we'll just get started. And yeah, anyone who joins late will just have to jump in. So just to get started here, we're going to be doing a lot of counting and probabilities today, as you can see on the screen. And the problems will get harder as you go. So if the problems at the beginning and all the teaching that we're doing at the beginning isn't hard for you, then don't worry, because by the end, we will be doing things that are very difficult. So you can always type in chat if you have questions or anything like that. You can also raise your hand, and then I will call on you if I see you most of the time if you have questions. And yeah, I think that's pretty much all I have. If you guys ever have questions, please just raise your hand, because that's going to make it a lot better. You guys can turn on your cameras if you want. You can leave them off if you want. I don't really care that much. But yeah, I think we're going to be doing a lot of fun problems today. We're going to be doing a lot of problems from past AMC tests. So hopefully you guys can learn a lot. And yeah. So I want this to be as interactive as possible, so you guys can always send messages in the chat about solutions that you have to questions, answers to questions, any questions you have at all. But yeah. All right, so I'll just get right into it. So the first thing that we're going to go over today is permutations. Permutations. So permutations, the most simple example of a permutation is How many ways are there to rearrange 5 different people in a line? So let's think about this question for a little bit. Hopefully this shouldn't cause you guys too much trouble, but let's say we have 5 people, A, B, C, D, and E, and they're in a line. Now, how many ways are there to rearrange this? Well, for the first person in the line, there are 5 options for that person, right? Because that person could be A, could be B, could be C, could be D, could be E. Now for the next person in line, there's 4 options because it could be any of the other ones. The next one has 3 options because it could be any of the other ones, and then 2, and then 1. Hopefully that should make sense to you guys. And then that's going to give it a total of 120 different permutations. And the reason why this is really important is because order matters. So unlike when you have combinations, which is something that we're going to learn about next, in this case, order is going to matter. So it's going to be different when you have E, A, B, C, D than like a different permutation of that. But as we'll see later, with combinations, order doesn't matter. So that was a pretty simple example, but let's do a little bit harder of an example. How many ways there are to rearrange the letters in the word Zoom? So now we have 4 letters as before, so we have 4 options for the first one, times 3, times 2, times 1 equals 24 total options. But now we have to do something else. We have to divide by 2. And the reason why that is let's say that our letters were like this, 0, 01, 0, 02, and then M. Well, now we can see that we counted every single one of these permutations twice because we counted this as something that's different than 02, 01, M. So we need to like think about the number of ways to rearrange the M's, and then we divide by that to get a total of 12. So our answer for this is going to be 12. And now, as I promised before, we're going to be hopping into the actual AMC 8 questions. So this is AMC 8 problem 14 from the year 2022. The actual problem was a little bit more difficult than this, but this is sort of what the problem looked like. And it said, how many ways can the letters in beekeeper be rearranged? So how many total letters do we have? That's the first thing that we're going to need to know. And we have 9 total letters. So 9 letters. And that means that we're going to have 9 times 8 times 7 times 6 times 5 all the way to 1 total choices. And then we need to think about the number of ways to rearrange those 5 E's because we counted it as if they were all different E's, but they're not. They're the same E, and we can't tell them apart at all. So there are 5 E's. So let's just like look at it like this: B, K, P, R, and then E, 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 and 2 more E's. This could be one permutation of this, and in this permutation we have 5 of these E's, right? And we can arrange those 5 E's in 5 times 4 times 3 times 2 times 1 different ways. So if you do this math, it's not very easy because it's 9 times 8 times 7 times 6. Oh no, I don't like doing mental math like this. 72 is 9 times 8 times 42 is 7 times 6. So then this is going to bring a total of... Yeah, that's not really the point of the problem. The point of the problem is that like you figure out how to divide by 120. But once you figure out that, I'm pretty sure this is the final answer. But if you couldn't do that multiplication, that doesn't matter too much because that is not the point of the problem. Alright, so now for you guys all who are here now, if you could just send in the chat like how you felt about that first slide, like good, okay, bad. That would be nice so I know how you guys are doing and whether or not to slow down or keep on going faster. Alright, so next we are going to be doing combinations. So this is very similar to the last thing that we did, the permutations, but this time instead of where the order always matters, the order doesn't matter. So the most simple example of this problem, similar to rearranging the 5 people in the last problem, is how many ways are there to choose 2 people from a group of 5 distinct people? Alright, so let's say we have 5 people, A, B, C, D, and E. And these people aren't too interesting of people because they just have one-letter names. But we need to select 2 people. So we have 5 options for the first person and 4 options for the second person. But now we need to divide by 2, because let's say we chose A as our first person and B as our second person. Well, we could have also just chosen B as our first person and A as our second person. So we need to divide by 2 to account for this thing right here. So 5 times 4, divide by 2, and this is going to be equal to 10. So that is going to be our answer for this little sample problem. It's going to be 10. And we don't care in what order we arrange the people we choose, right? Because BA counted for the same thing as AB. So you really need to keep that in mind, because a lot of times that happens in problems like this. And combinations relate to Pascal's triangle, which we will get to later. But this sort of special thing where we choose a certain number of people from a certain group of people is something that we're going to be facing a little bit later. All right, so Alice has 24 apples. In how many ways can she share them with Becky and Chris so that each of the 3 people have at least 2 apples? So as you see, this is a problem 25, which is pretty incredible because, I mean, problem 25, that's the hardest problem in the entire test. So already we are getting to pretty difficult problems. So Becky and Chris and Alice all need to have 2 apples, no matter what. So we can just give them those 2 apples right away. And basically now we have to do Alice, let's say A is Alice's apples, and then B is Becky's apples, and C is Chris's apples. When we sum up all of them, they're going to have to equal 18. Besides the 2 ones that we just gave them. So they're going to have to equal 18. And that means now that we just need to figure out this problem. These are all positive integers or non-negative integers because they could be 0. And we need to figure out how many ways are there to assign numbers to A and B and C such that they sum to 18. Well, I'll introduce you to a little concept here. How about we put like dividers right here, okay? And let like this be the apples, these be the apples. And obviously I didn't draw 18, but just imagine that there were 18. So we need to figure out the number of ways to rearrange the dividers and the apples. And the reason why this works is because, think about it. The one on the leftmost side of the dividers is going to be the ones that Alice has. The ones in the middle of the dividers is going to be the ones that Becky has. And the ones on the very right of the dividers are going to be the ones that Chris has. So this perfectly corresponds to A plus B plus C equals 18. So now we just need to figure out the number of ways to rearrange 18 apples in 2 of these dividers, and that's going to be 20 total objects we have here, and we need to choose 2 of them, okay? And this is equal to 190. So yeah. Oh no, I wrote over myself. 20, and this is going to be equal to 190. Okay, so if you don't know what this thingy means right here with like these little brackets, that's just saying that we're choosing 2 of the objects out of 20 of the objects, and the 2 that we're choosing is going to be the dividers. So this is called stars and bars, and yeah, it's a pretty useful concept if you don't already know it. So something that will definitely be useful on the AMC 8, and yeah, just in general, it's going to be useful in all math competitions. All right, so those are our first 2 slides. And yeah, if you guys could just let me know how you're doing in the chat. If you guys are following me, you could like put a thumbs up in the chat just anyway so I can see how you guys are doing and if you're following along or not. If you don't want to put anything in the chat, that's okay too, but it always helps me out. All right, so the next thing we are going to be doing now is, and I'm seeing a lot of goods in the chat, so that's great. That means I'm not going too fast, so I'll continue going at this pace. All right, so now I'm going to be doing problems with conditions. And this is really, really vague, but you'll see that in the AMC 8, there are a lot of problems that are pretty similar to this. So When there are conditions in a problem, account for the most restrictive condition first. And I bet none of you guys have any idea what I'm talking about. Maybe you do, which would be great. But if you don't have any idea what I'm talking about, that's completely okay. What we're going to do now is walk through a little bit of what I mean by this. But the easiest way to see this is by doing problems. So there's no like specific thing that we're learning here. We're just going to be doing some problems and seeing how this sort of theory applies. An integer between 1,000 and 9,999 inclusive is chosen at random. What is the probability that it is an odd integer whose digits are all distinct? Okay, so we need an odd integer, and all of the digits have to be distinct. Well, I think the most restrictive thing about this is that it has to be odd, because when a number is odd, that means that the last digit is 1, 3, 5, 7, or 9. 1, 3, 5, 7, or 9. So we have 5 options for that last digit, okay? Because we have 4 total digits, and the last one has to be 1, 3, 5, 7, or 9. So notice how we started with the most restrictive digit. If we had started with one of the middle ones, it would not be as good. And now the next most restrictive digit is going to be the first one, because the first one can't be 0. The other ones can be anything from 0 to 9, but this first digit right here can only be 1 through 9. And now we only have 8 options for it now that we chose one of the numbers that are 1 through 9. So we have 5 times 8, and now let's go on to this digit right here. We have 7 options for this digit because we have already chosen, oh sorry, not 7, I take that back. 8 options. So we have 8 options for this digit here now because we chose one of the digits for our first digit and one of the digits for our last digit. So that means that we have 8 digits remaining, so 5 times 8 times 8. And then we have already chosen 3 digits once we get to this final digit. So we need to multiply it by 7 to get our final answer. And this is not an easy multiplication, but doing it in my head, I believe it goes to 2,240. So that is going to be our final answer. And that was a problem 20. So it's a pretty difficult problem on the AMC 8. But if you just use the most restrictive condition first, then that's going to be helpful. So if we had tried, for example, to say how many options are there for that first digit, right? If we had said, I want to figure out what this digit is first, then it would have been pretty difficult because we would have not been able to account for the odd digit very well because we could have maybe chosen a 1, 3, 5, 7, or 9, or maybe not. So remember to must start with the most restrictive thing first. Alright, so now AMC 8 2018 problem 11. Abby, Bridget, and 4 of their classmates will be sitting in 2 rows of 3 in the picture as shown. So I didn't attach the picture, but basically the picture showed like this. That's all it showed. If the seating positions are assigned randomly, what is the probability that Abby and Bridget are adjacent to each other in the same row or the same column? So we need them to, be somewhere adjacent to each other. Notice how like the 4 classmates like don't really matter at all in this problem, right? These guys don't matter at all. So we're just gonna get rid of them, like completely basically from the problem. So now we have conditions. So I'm gonna say that we are going to put Abby and Bridget next to each other and then see how that plays out in the actual thing. So they could either be in columns. If they are in the same column, then they're going to be like this. So let's just say that Abby sits here. Notice how Bridget will now have 5 total seats to account for. She has 5 total seats to account for. And only 3 of them are going to be in the same row or same column as Abby. So that means that 3 over 5 of the seats are going to work in this case. And for every single place that Abby sits, no matter where she sits in any of these 6 seats, Bridget is always going to have exactly 3 options for where she can sit so that she's going to be in the same column or same row as Abby. So 3 over 5 is actually going to be our final answer. And this doesn't relate to the problems as conditions as much as the other one, because we don't necessarily have conditions and more restrictive and less restrictive ones, but it is a very good problem to focus on. Okay, so now we are going on to the next topic in the workshop. So our next topic that we have is probability. Probability is the number of successful outcomes over the number of total outcomes. Number of successes over total. All right, so basically this means that you just have to count the number of ways to be successful in a problem over the number of total ways. So count the total ways and then the successful ways, and then you will have solved the problem just like that. So a lot of times probability is just two counting problems. And what I mean by counting is a lot of like the combinations, permutations. It's going to be two of those problems. So once you realize that, you'll realize that probability problems are really not that difficult. They're a lot easier than you think. So AMC 8 2020 problem 13. Jamal has a drawer containing 6 socks, 6 green socks, 18 purple socks, 12 orange socks. After adding more purple socks, Jamal noticed that there is now a 60% chance that a randomly selected sock from the drawer is purple. How many purple socks did Jamal add? Okay, so right now, the first thing I'm going to do is count the amount of total socks and then count the amount of purple socks and see how many we have to add. So 6 plus 18 plus 12 equals 36. Yes, exactly. 36 total socks. So we have 36 total socks and we have purple socks, we have 18. So right now we have a 15% chance. But we need to add something. Okay, not 15. Sorry, 50% chance. So we need to add something so that we have a 60% chance. So yeah, we need to add something to both the top and the bottom. And basically that means that we'll have 18 non-purple socks. So 18 is how many non-purple socks we'll have, and 18 over something is going to have to equal 40% or 0.4. So now this is really just going to be algebra here, and we will see that x is going to be equal to, oh no, wait, hold on. 6 green socks, 18 purple socks, and 12. I must have, let me see here. I think I messed something up. Hold on. So 18 purple socks plus some amount of socks over 36 plus some amount of socks is going to equal to 0.6. So 18 plus x is equal to 21.6 plus 0.6x. Okay, here we go. So now 0.4x is going to equal 3.6, and x is 9. So we're going to need to add 9 purple socks. And for some reason when I did it the other way up there, it didn't work. Yeah, I don't know what I was doing. Okay, yeah, I think I understand now. Alright, but basically this is a lot of algebra, right? But the most important thing to realize is that the number of successes over the number of total socks is going to be our answer. So for probability questions, and we can use algebra in this case to figure out that if you add 9 purple socks, then your answer will be correct. So now we have AMC 8 2019, problem 18 for our next probability problem. Okay, the faces of each of 2 fair die are numbered 1, 2, 3, 5, 7, and 8. When the dice are tossed, what is the probability that their sum will be an even number? Okay, what is the probability that will be an even number? So what you care about most here is whether a number is odd or even. So looking at it, we have 4 odd numbers and 2 even numbers. 4 odd and 2 even. Okay, so we have to figure out when 2 of these dice are tossed, what's the probability that their sum will be an even number. So in order for the sum to be an even number, we could either have an even number and then another even number, or an odd number and then another odd number. So we have 6 faces, so we have 6 times 6 equals 36 total outcomes. And now for successes, we have, if it's even and 2 even numbers, then we have 2 options for the first even number and 2 options for the next one. Or if it's odd and odd, then we have 4 options and 4 options for the next one, because there are 4 odd numbers and 2 even numbers. So we have 4 for 2 even numbers and 16 for 2 odd numbers. So this brings us to a total of 20 different choices for even, or odd. And that's exactly what we want, because if we have an even and an odd, or an odd and an even, then that's not going to be a success, because that would lead to an odd number. So 20 over 36 is our final answer, and simplifying that, we get 5 over 9. All right, so 5 over 9 is the probability that their sum will be an even number. And notice how we didn't have to do any of all the casework and be like 1/6 probability that it's 1 times 1/6 probability that it's 5, and that's going to give us one case, and that's 1 over 36. But we just jumped straight into successes over total, and that's always how you do probability, because that's how you're going to figure out the problems faster. Okay. All right. Now we're going to switch into the next couple topics here at the end of the workshop. Will be more difficult than the ones at the beginning. So what we're going to be covering now is casework. And casework is the most important of the topics we will cover today, because casework comes up incredibly frequently in AMC 8, and you can solve basically every single problem in AMC 8 that has to do with counting and probability if you're good enough at it. But that would have to be really good, but still, you can do that if you are good enough at it. And it's more of a general idea, because there's no hard things you need to learn. You just need to become more fluid in organizing your thoughts and your cases, and I don't know, there's a lot of different things that can help you be better at casework, but it's very important for the AMC 8. So AMC 8 2024, problem 13. Buzz Bunny is hopping up and down a set of stairs, one step at a time. In how many ways can Buzz Bunny start on the ground, make a sequence of 6 hops, and end up back on the ground? All right. So there's a set of stairs, and there's a bunny thing right here. Let's just draw it like this. And it can move up or down the thing. So we're going to need to make 3 ups and 3 downs. All right? So now the most important thing we need to be careful of is that we can't have at any point more downs than we have ups. So we can't have up, down, down, up, up, up. That's something that we can't have ever. So we need to make sure that never happens. So now I think the easiest way would be to just list them all out, but I don't really want to do that, right? Because that's kind of annoying. So let's say that we start, okay, one second, I'll move to the next thing. Let's say we start with up, down. Then that means that the next one has to be up, because otherwise everything would be bad. And now for the last 3, we have 3 different options, because we have 2 Ds and we have 1 up. So we have 3 different options, and 2 of them are going to work. The only one that won't work is if up is on the last one. So for the case where we start with UD, we have 2 total options. All right, now say we started with up and another up. In this case, we have 3 Ds remaining and 1 U, and we have 4 total ways to arrange them now, but we only count 3 of them because We don't want the one where the thing ends in U. So we have UU is 3, and UD, when we start with up down, that's going to be 2. So we have a total of 5 different cases now. And that's going to be our final answer. So yeah, we just did casework split up into the different times when we start with up down or we start with up up, and that's going to help us solve problems a lot. And yeah, now we're going to get into a little bit more difficult casework problems, and these are going to be some of the most difficult problems you will see on the AMC 8. Okay, so Alana writes the numbers 1 through 9 on separate cards, one number per card. She wishes to divide the cards into 3 groups of 3 cards so that the sum of the numbers in each group will be the same. And how many ways can this be done? Okay, so we need the sum of the numbers on each card to be the same. So the first thing that we need to do is we need to figure out what this sum is right here. 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9. Okay, when we sum up all of these, we get 45. So if we want the sum of the numbers in each group to be the same, then that means that we want the sum of those numbers in each of those groups to be 15, okay? So 15 for each group. All right, 15 for each group. So that means that now we have to figure out the groups in such a way that they sum to 15. So let's just like find a bunch of different ways that we can make things sum to 15. And notice how like these 3 groups are like indistinguishable, if you will, right? So like if we have the same numbers in each of the 3 groups, but we like rearrange the groups, like no one cares. So like no one cares about the order of the groups. So yeah, but let's say we have 1 in one of the groups, then we could have 5 and 9, or we could have 1, 6, and 8. And those are the only ones we can have with 1. So now let's say we have 2 in a group. If we have 2 in a group, let's say we have 4 and 9, or 2, 5, and 8, or 2, 6, and 7. Now let's say we have 3 in a group. And Will Wen says 6, 7. Yes, we have 2, 6, 7. All right, now let's say we have 3 in a group. With 3 in a group, we have 3, 4, and 8, and 3, 5, and 7. So this seems like pretty exhausting so far, right? Because we just have to list out all these groups. So I think the way that's going to be easier to do it is we just think about like when we have 1, 5, and 9. Or we're going to need to put 9, we're going to need to put 1 in one of the groups. So let's just say 1, 5, 9 is one of the groups, and let's say 1, 6, 8 is one of the groups, and that's 2 different cases, and that's actually going to be our entire problem, because those are the only 2 groups that 1 can possibly be in. Now, since 1 is like the extreme low, let's look at the extreme high. If we have 9 in a group, then we could have 5 and 1, as we've seen, or 9, 4, and 2. And these are actually the only groups that 9 could be in. So we have 9 in this group, but over here, we would need 9, 4, and 2 to be one of the other groups. And the last group over here would be just all of the other numbers, which would be 3, 5, and 7. So this is one of our answers, and it looks like we're not going to get very many answers, if any at all. So now we have to look over here. We have 2, 5, and 8, or 2, 6, and 7. And this one won't work with this case over here. This one won't work either because there's a 5. So this is the only case. So 2, 6, and 7. And then we have to add 3, 4, and 8 to that as well. So this is going to be our other answer. And that gives us a total of 2 answers, which I believe is the answer to the problem. Okay, yes. 2, is our final answer. So yeah, we just did some casework, and actually the answer in each of those cases was 1, but we had to list out a lot of things in order to solve that problem, and a lot of times you have to do that with casework type of things. So now we're going to move on to AMC 2022 problem 23. So form a regular octagon. From a regular octagon, a triangle is formed by connecting 3 randomly chosen vertices of the octagon. What is the probability that at least one of the sides of the triangle is also a side of the octagon? So the first thing we're going to do is figure out how many total triangles we can choose. So what we're doing is we're choosing 3 of these vertices to be part of the triangle. Okay? So 3 of these vertices are going to be part of the triangle, and that means that we're going to be doing 8, choose 3. So this is what we learned from combinations earlier, and I know we went over it very fast, but we have 8 options for the first vertice, 7 options for the next vertice, and 6 options for the last vertex. But we could have rearranged how we chose those. So like, let's say we chose this one first, then this one, and this one. We counted that as the same thing as choosing this one first, then choosing this one, and choosing this one. We counted those as different things, but in reality, they're the same thing. So we need to divide by 3 times 2 times 1, because that is how many ways we over. Oh, you guys can't see that, but 8 times 7 times 6 over 3 times 2 times 1. So this is going to be equal to 56. So there's 56 total ways. And now we just need to figure out how many of those ways have it so that the triangle does not have the side of the octagon as one of the sides. So there are 2 different cases for this triangle. Okay, that's a terrible octagon, but I think we should get the point, hopefully. So let's say like this kind of thingy. So notice how it's kind of a right triangle, right? A 45, 45, 90 triangle. And this is one case, and we can rotate this around 8 different times to get 8 different triangles, right? Because think about it. We could have the vertex that is right here. We could have it in any of the 8 vertices, and we would get a different triangle. So we have 8 successful outcomes there. And then there's one other case, and I'll draw another octagon to show this other case. For the other case, that's even a worse octagon, but for the other case, we have like this kind of a triangle. It's like an isosceles triangle, okay? And once again, we could put that vertex right here, we could put it at 8 different of those things, and we would have another triangle. So that's 8 plus 8 divided by 56, and that's going to be 16 over 56. So our final answer is 2 over 7. Except for we counted the probability that at least one of the sides of the triangle is not a side of the octagon. We counted the probability that every single one of the sides is not a side of the octagon. And that is a technique used called complementary counting. So you guys may have been a little bit confused there because you were like, aren't you finding ones that don't have any of their sides as a side of the octagon? But that is indeed what I was finding. So the answer is not going to be 2 over 7, but actually 5 over 7. So if you guys don't know what complementary counting is, that's exactly what it is. It's counting like what we don't want instead of what we want. Because if we were to try and find all the triangles that had their side as one of the octagon sides, then it would be pretty difficult to do anything with this problem. So you need to, it's a lot easier sometimes to figure out what doesn't work instead of what does work. And that's what we did here. So yes. All right, hopefully that makes sense. If you guys, I know we are doing some harder problems now, so if you are understanding, you can write like a good in the chat. If you're not, you could be like, I have a question, or you could be like, raise your hand or something, you know. But if not, you can always just type good in the chat if you're understanding. So that would be great, just so I understand a little bit if you're understanding or not. All right, so we are going to be continuing now with some more of these harder counting concepts. So Constructive counting is our next counting concept. So in this kind of counting, you construct something that satisfies the condition and figure out how to replace it. This is more intuitive than many other types of problems. Okay, so constructive counting maybe sounds a little like terrifying and scary, but it's really not that bad. It's not too difficult, so hopefully you guys should understand how to do it. But basically what it is constructive counting is where you construct things, okay? So let's read this problem. AMC 8, 2024, problem 17. So a chess king is said to attack all of the squares one step away from it, horizontally, vertically, or diagonally. For instance, a king at the center of a 3x3 square attacks all other figures as shown below. So I didn't write the diagram as I said before with the other problem, but in this case it's very similar to the other problem where it's really not that difficult just to draw the diagram. So when we have the king in the center, it's going to attack all of the other squares, but in this case we have to have the king somewhere else, because what we want is that suppose a white king and a black king are placed on different squares of a 3x3 grid so that they do not attack each other. And how many ways can this be done? Alright, so let's construct one way. So let's say that we put the black king right here. So now we can put the white king not here, not here, not here, not here, not here, but we have to put the white king here, here, or here. So we have three different ways when the black king is in that corner. And what we actually have is 4 of those corners. Okay, sorry. 3 times 4 total corners. And that is going to be equal to 12 different options. But that's not the only way that we could have it. We could also have it where we are on like one of the sides kind of thing. Right? Alright, so if we are right here, then the white king could be right here, here, or here. And that's also 3 different options. And we multiply by 4 because we have 4 different places that the black king could be. So again, we multiply 3 times 4, and that's going to be equal to 12. So this is going to be a total of 24. Yes, and that is going to be our final answer. So Bay says, wait. Can't the white king be on the other corners? Wait, I don't know exactly what you mean by that. Do you want to like unmute and maybe like tell me a little bit more?
So it can be on the top right and the bottom left as well.
Okay, yeah, I think I just didn't explain myself well enough. Okay, so basically what I mean, sorry, I did not explain myself well enough. So the black king, when it's in the top left corner, we have 3 different options for the white king. We already established that, right? And when you have it in any of the other corners, you're also going to have 3 options because it's going to be exactly the same as that corner. There's nothing unique about this corner. So we are going to have 3 different options because we have 3 options for the white king, and then we have 4 different options because there's 4 different corners that the black king could go to. So that's why we multiplied by 4 over here. Does that answer your question and like account for the thing? So when we have 3 different places that the white king could go when we put the black king exactly there, and we have to multiply it by 4 because the black king could go here, 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 or here. So there's 4 different places that the black king could go to, and same with the corners. The black king could go to this corner, this corner, this corner, or this corner. So that's 24 now. Does that make sense now?
Not really, because the black king doesn't attack like all the way to the top.
Oh my word, you're so right. Okay, sorry, my fault, yeah. I didn't understand what you were trying to say. Okay, yeah, that's my fault. Yeah, so yeah, I forgot about that case of the thing. So yeah, it's going to be 5 times 4 instead of 3 times 4. So 5 times 4 is equal to 20. And yeah, 20 and 12. So yeah, 32. Thank you so much for pointing that out. Yeah, I got that wrong. 32 is going to be our final answer. So yeah. Yeah, you have to construct it so that we account for all of the places that the White King could be, and I made a silly mistake, but the answer should be 32 and not 24. Alright, moving on to the next topic that we're going to be doing, and we have this and one more, I think. Yes. But this one might take a little bit longer than the other topics. So, counting paths with Pascal's triangle. So counting paths can be done with combinatorics, but there's an easier way to use Pascal's triangle. So if you don't know what Pascal's triangle is, it's this triangle thingy that's like 1, 1, 1, 2, 1. And basically you sum up the two numbers above it in order to get the number below. And it's really useful, and it shows a lot about combinations and stuff. But I can't really get into that now when we just have an hour. So I don't know, maybe you could like meet with me privately to figure out more about that. But 1, 1, 2, 1, 1, 1, 3, 3, 1, and it relates a lot to finding paths on a grid. So I'm going to give a very simple example problem before we get into that much harder looking problem right there. Let's say we have a 3 by 3 grid. Oops, terrible 3 by 3 grid. Let's say we have a 3 by 3 grid, and we want to go from the bottom left to the top right. Alright, so we could go, and for every step that we make once we start at A, we could go left or right. But we can't go anywhere else. So we have to go left or right for every single step that we have. Okay, so, wait, no, did I say left or right? I meant right or up. So we can go right or up for every single step that we have from A. So we have to go right 2 times. And we have to go up right 2 times and up 2 times. Alright, so once we do this, then we're always going to be at B when we go up right 2 times and up 2 times. So that means that all we have to do is like think about it like this: right, right, up, up. And we just have to rearrange these. So that's a total of 4, choose 2 different ways to do that, because we have 4 times 3 times 2 times 1, and we divide by 2 twice. Okay, so that's 4 times 3 times 2 times 1, divide by 2, divide by 2, and this is going to be equal to 6 different ways that we can do this. So we have 6 different ways that we can go from point A to point B. So we just need to figure out a little bit more, a different way to do this. So the next thing we're going to do is we're going to approach this problem in a different way. Alright, so how many ways are there to get to this point right here? Well, there's one way to get there, and there's one way to get here. How many ways are there to get to this top point? One way, and one way. And then there's 2 ways to get here, 3 ways to get here, and 3 ways to get here. So wait, how was I doing all this so fast? Well, think about it. Okay? Actually, first we're going to clear the screen a little bit so we can get a new diagram. Okay. So we want to go from A to B. Okay, that's actually a small one. I'm going to go over here with a bigger one. So we want to go from A to B, right? And we need to go up and right every single time. So in order to get to this square right here, we have to go up. There's nowhere else that we can go. We can't go anywhere else. In order to get to this place right here, you have to go right. There's nowhere else that you can go. And in order to get to this square right here, you have to go right again. So there's one way to get there and one way to get here. Now, in order to get to this square right here, you have to come from either this square or you have to come from this square. So that means that we could either come directly from this square, in which way there's one way to get there, so then there's going to be one way to get here, or we could come from this square, in which case there's one way to get here, so there's one way to get here. So that's 2 total ways to get to the center square. And then we have to come from either this square or this square to get to this square. And there's 2 ways to get to this square from this square. So then there's 2 ways to go to this square, plus 1 way to get to there, so that's going to be 3. And then there's also going to be 3 over here. So there's 3 ways to get to here, there's 3 ways to get to here. That means that there's going to be a total of 6 ways to get to this top right here. And now that's exactly the same way that we did exactly the same answer that we got last time. So we can be pretty confident that our 6 is correct. All right. So that's how you do counting paths with Pascal's triangle. And we didn't really talk too much about what Pascal's triangle is, but Pascal's triangle is this thingy right here that we found over here with all of these numbers. Okay. So now AMC 8's 2020 problem 21. A game board consists of 64 squares that alternate in color between black and white. The figure below shows square P in the bottom row and square Q in the top right row. A marker is placed at P. A step consists of moving the marker onto one of the adjoining white squares in the row above. How many 7 steps are there from P to Q? Alright, so I have the figure here as well as the problem statement again. So we need to find some path to go from P to Q. It's going to be only on these white squares, as we can see. Or gray squares, I should say. So how many ways are there to get to this point right here? Well, there's 1 way to get to this point. We have to go diagonally to the left. And there's also 1 way to get to this point. And 1 way to get to this point. And 1 way to get to this point and this point. So as we can see, all we have to do is add up the 2 numbers below the point. Because that's the only way to get to that point in specific. So there's going to be 2 ways to get to this point. 3, 4. 3 ways to get here. 3 ways to get here. 6 ways to get here, then 10, and you can just fill out all the things by adding up the 2 numbers below it. And what you get is a total of 28. So that was pretty fast actually compared to any other way that we would have had to do it. Because if we had to do combinations, we would have had to account for like the missing squares over here, because there are missing squares over here. That would have caused us some trouble. But in this case, it really just helps that we know how to do this problem just by putting up with the Pascal's triangle. Okay, so now for the, can you guys just tell me one more time if you guys are doing okay? Because I know we're covering the harder problems of AMC 8. Like this is a problem 21, so not the easiest problem, but you guys can put like good in chat or like whatever you want. Just to make sure that no one's really struggling and has questions and stuff. But if you do have questions, you can always raise your hand or something to ask those questions. Alright, if everyone's doing good, that's great. So, the hardest, now we're going to be going over just generally advanced problems on the AMC 8. So the hardest problem, the AMC 8 will simply apply the topics we just learned, all of the topics that we just learned, and they'll just do it like in a new way. So don't be scared of like the problems, because most likely, like, you know how to solve them. They're just like thinking about things in different ways. So the solutions will not be impossible, which is nice to hear because we don't want to do impossible problems. But yeah, most of the solutions will not be impossible. All of the solutions actually will not be impossible. It just like seems pretty hard sometimes. All right, a top hat contains 3 red chips and 2 green chips. Chips are randomly drawn 1 at a time without replacement until all 3 of the reds are drawn or until both green chips are drawn. What is the probability that the 3 reds are drawn? So we have like 3 red chips and 2 green chips in the hat. Let's just like think about it like this. And these ones are red and these ones are green. We need to figure out what is the probability that we draw the 3 reds before we get the 2 greens. So this is really, really interesting, right? Because we don't know anything else, but we do know that we're going to stop once we get that kind of thing. So let's just say that we drew a red one first, and then like a green one, and then like a red one, and then a red one, and then a green one. Well, actually, the interesting thing about this one is that we would stop right here, right? But we can kind of think about it like this, right? We can kind of think of it as like choosing an arrangement of these 5 different things and then figuring out which one of them pertains to which, because these is just going to be like a rearrangement of those integers, and in any way we do it, that's how we're going to draw the chips. So in this case, what we are thinking about when we do this is we're going to just draw the red one first, and then we're going to draw the green one, and then we're going to draw the red one, and then the red one, and then the green one. But notice how like the last one that we drew was green, and because it was green, that meant that we drew the red ones first. Okay. So let's just do like one more example of this. Let's say it's like, all right, so now we would stop right here, but we just drew these 2 extra R's at the end for fun. Oh, sorry. You can't see that. So now what would actually happen in the problem is we would stop right there, but we just drew these 2 extra R's at the end for fun. And because the last letter is R, that means that we're going to have the green ones drawn first. So basically what I'm saying is that we arrange these letters, green, green, red, 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 and whichever one is the last one of this set of 5 letters, that's going to be the one that we don't draw. So what we need is that we need green to be one of the last letters, to be the last letter, sorry. And the probability that happens is 2/5. So that's literally going to be our answer. Basically, what we did here is we didn't do any of the busy work of the probability. We just noticed something really, really cool. If we line them all up in like a row and then just take them one at a time, basically. So that's what this is, right? We're just lining them up in a row and saying, oh, I'm going to take the green chip first, then the green chip, then the red, then the red, then the red. Whichever one we take last is not going to be one of the ones that's drawn. So think about it like that. Like, it's a different way to think about the problem, right? Because if you line them up in a row, that's not taking them out of a hat. But it's going to be something that is, yeah, pretty cool, and a different way to frame the problem. So in this case, we get 2 out of 5. All right, I think we have 2 more problems, and they're both AMC 8 problem 25s. And these are both very, very difficult problems, so don't be worried if you can't solve these problems. And then we'll be done today. We have some things to do at the end, and yeah, but we're coming down the home stretch now. So an airplane has 4 seats of 3 rows. 4 rows of seats of... Okay, never mind. An airplane has 4 rows of seats with 3 seats in each row. 8 passengers have boarded the plane and are distributed randomly among the seats. A married couple is next to board. What is the probability that there will be 2 adjacent seats in the same row for the married couple? So basically what we have here is we have 3 of these. And actually I'm going to go back to the problem just so you guys can like see it for a little bit longer before we go over here. So we have 12 seats and 4 rows. So the first thing we're going to do is we need to choose 8 of these 12 seats for the passengers to sit in. And then we need to figure out the successes over the total, right? So this is the total, right? We have the total for 12, choose 8. And then we need to do casework, which is also something we did. Probability, casework, 2 of the things we did. And in order to figure out what is the probability that we have the married couple have a row where they can sit next to each other, right? All right. Let's go to the next one now. Okay, so we have 8 people, and 12 choose 8 is going to be 12 times 12 times 11 times 10. I'm just going to do it real quick for you guys here. 12 choose 8 is going to be 495. So we have 495 ways for them to sit in total in this thing. And we need it so that there is one row or more than one row where one person is sitting in that row. So, or 0 people. So we could have 0 people sitting in a row. So we could have 3 people sitting in one row, 3 people sitting in another, and then 2 people in one of those rows and 0 in another. Or we could have, because if we have 2 people, at least 2 people sitting in every single row, that's not going to work for us. So we need one person sitting in some row for this to work. So we could have 3 people sitting in one row, 2 in one row, 2 in another row, and 1 in the last one, or we could have 3, 3, 1, and 1. But we need to be careful when we have one person sitting in a row. Because when we have one person sitting in a row, we need that person to be sitting on one of the ends of the row, okay? So this looks like it's going to be pretty difficult. That's because it is going to be difficult. So when we have 3, 3, 2, and 0, we have 0 ways to arrange these 3 people, or 1 way, I suppose. 1 way to arrange these 3 people in a row, and 3 ways to arrange those people in a row. So we have 3 people to arrange those people in a row, and then we have to permute these 3, 3, 2, and 0, because those could be any of the 4 different rows. So we have 4 times 3 times 2 times 1, and we have to divide by 2 because these 2 3's are the same, and those can be in the same row. So 4 times 3 is 12. So 3 times 12 is the total number of ways that we can do for this case right here. All right. Now 3 times 2 times 2 times 1. So we have 3 options for the row of 2, 3 options for the other row of 2, and for the row of 1, we have to have it sitting on this end or this end. So we have 2 options for that one, but we can't have it in the middle, because if we have it in the middle, then that is going to be not work with us here. So 3 times 3 times 2, and then we have 12 ways to permute these numbers among the rows. So this is going to be our other case. And now we have one more case. Notice that the number of ways to do these two is we have 3 options for each of them, because one of them could be in the middle actually, but we just need the other one to not be in the middle. So they just need to not both be in the middle. So we have 8 total cases for that. So 8 number of ways to rearrange the people in each of these rows once they're at 3, 3, 1, and 6 ways to permute them to get them 3 to 3, 3, 1, because 4 times 3 times 2 times 1 divided by 2 divided by 2. That's going to be 6. So this is 36. And then this is going to be 216 if you multiply it out, and this is going to be 48. So if you add up all of these, you should get, hold on here. This is pretty difficult addition. 84 plus 216. 300 over 495. 300 divided by 495 is going to be equal to, 1 second here. This is pretty not easy. 60 over 99, or 20 over 33. So that's going to be our final answer, actually. And I know that was not easy, right? Because this problem is really just not easy in general. But if you do all the casework and do all the multiplication, then hopefully it should not be as difficult as it looks on the surface. And we have 2 minutes left in our thing, but I think that's all that I'm going to be doing for now. We're going to skip this last problem because I wanted to talk about how to prepare for the upcoming AMC 8. And I know it's all like less than 2 months away, so it's not that close, but if you guys want, you can always contact me for teaching like this, because I really, really like teaching people individually. Some of the people in this workshop, actually, I already do tutor one-on-one, so it would be really great if you guys could email me just to reach out, and for more one-on-one tutoring like this, you can ask your parents for anything like that if you want. I have flexible rates, so don't worry about like how much it costs or anything like that. But I have extensive experience teaching middle schoolers, and I really, really like doing it. So if you guys could email me, and you can, that's my email right there, so you can do that, or you can always look back to my website, because it's pretty easy to contact me from there. But that is all that I have for today. So if you guys have questions about any of the problems or anything like that, then you guys can unmute and ask the questions, raise your hand. If you have questions about how tutoring would work, one-on-one tutoring that I do a lot of, you could also ask me about that. Or if you have questions about any of the upcoming workshops, because we're going to be doing 3 more workshops that are very similar to this. So if you guys are excited for that, then you could sign up for those as well. But if you guys don't have any questions, I think you all are free to leave. And thank you guys so much for coming. It means a lot to me when a lot of people show up for something like this. So thank you guys so much for coming, and I'll see you at the next workshop next week, hopefully. But that is all I have, and you guys are free to leave. So bye, everybody.
Bye.
Bye. Jeremy, did you have any questions?